In this video, we will talk about how to compute partial derivatives. So I want to begin with the definition of what a partial derivative is, very formally. So if I let f of x comma y be a function, then del f del x. So this is the partial derivative of f with respect to the variable x. And there's a limit definition for what this is. It's the limit as h approaches 0. And it's really similar to the limit definition of a single variable function. There's an h on the bottom, and there's f of something minus f of something on the top. But in this case, we have a multivariable function. So instead of this second thing just being f of x, it's going to be f of x comma y. Okay, but when we take the partial derivative with respect to x, as we saw in the last video, what that means is we're holding y constant. We're not letting y vary. So the y coordinate even here should be the same. It should just be y. But we are letting the x vary. So for the x coordinate, we will write x plus h. And that's, let me just space it out a little bit more. X plus h comma y. That's the limit definition of the partial derivative with respect to x. So this is a really similar definition for del f del y. It's the limit as h approaches 0, f of x comma y plus h minus f of x comma y all over h. Okay, and if I had a function of 3 or more variables, we could generalize these limit definitions. So we could generalize these for 3 plus variable functions if we needed to. All right, so I'm going to focus the rest of this video on actually computing some partial derivatives. Okay, so in practice, if we want to compute, first let's do del f del x. What we do is we treat x as a variable and hold other variables, any other variables that are in the function, constant. So if I have a 2-variable function, as we did up here in this definition, I would just be holding the y constant when I find the x partial derivative. Okay, so similarly, if I want to find the partial with respect to y, we would treat y as a variable and hold any other variables constant. All right, so let's do an example to see what this looks like in practice. So here's the first example. Let's say f of x comma y is 20 minus x squared minus 2y squared. And I want to find the partial derivatives with respect to x and with respect to y at the point 1, 2, 15. So that means x is 1, y is 2. And, oh, whoops, I think there's a mistake here. This shouldn't be 15, it should be 11. The way I get the z coordinate is I would plug in 1 for the x, I would plug in 2 for the y, and that gives me 20 minus 1 minus 8, and that gives me 11. All right, so let's find these partial derivatives. All right, so let's start with a partial derivative with respect to x. So when we do this, the 20 is a constant, so that derivative is 0. When we take the derivative of minus x squared, because we're taking the partial with respect to the variable x, that means I do treat x as a variable. So the derivative of that is just minus 2x. Okay, but then when I get to the minus 2y squared, that gets treated as a constant. When I take the partial derivative with respect to x, we are treating all other variables, that includes y, as a constant. And the derivative of a constant would be 0. So I would get minus 0 there. That is super, super important. If you're unclear on why this is 0, I definitely encourage you to pause the video and think about that on your own for about 30 seconds. We'll see that a bunch over the course of this video and the next video. Okay, so we'll get plenty of opportunities to practice this and get used to it. All right, so simplifying this, we just have negative 2x. All right, but we wanted to evaluate this and plug in x is 1 and y is 2. I don't write the z-coordinate here. Actually, let me say it this way. I don't need to write the z-coordinate here because with my function is a function of two variables. There's an x and there's a y. So the input for my function is it just consists of the point that has the x-coordinate and the y-coordinate. So if I plug that in, we'll get negative 2 times 1, which is negative 2. All right, so that's the partial derivative with respect to x at this point. All right, so next let's do the partial of f with respect to y. So if we do it with respect to y, so the 20 still gets treated as a constant, so the derivative of that is 0. Now I'm treating y as the variable and x as a constant. That means minus x squared is a constant, so its derivative should be 0. So minus 0, and then when I take the derivative of minus 2y squared, now I am treating y as a variable, so I get minus 4y. Awesome. Now let's plug in our point. So we'll get del f del y. Whoops, let's plug in the point. X is 1 and y is 2. If we plug that in, we get negative 4 times 2 plugging in for y, and that's negative 8. Okay, so those are our partial derivatives right there. So one thing that I want to note about this is, in general, del f del x and del f del y are different. So in general, in practice, the partial derivatives with respect to x and the partial derivative with respect to y, they're going to be different. So now there might be certain exceptions where they're the same, but in general, in most cases, they're going to be different. And that showed up here in this example. All right, so next I want to just talk about some notation to talk about partial derivatives. So we can write the partial of f with respect to x in the following ways. So there are maybe 3 other common notations that we'll see for this. So sometimes when I have a variable of 2 functions, we call f z. And if we call f z, we could write it as dz dx. So that's specifically for a function of 2 variables. I could also write, there's sort of like a version of the prime notation, if you remember from calculus. If you remember from calculus, there's like there's a df dx notation, and there's also like a prime notation. So the version of prime notation for partial derivatives is we write f, and then we write the variable that we're taking the derivative with respect to as a subscript. So I write fx like this. Okay, and then again, if I have a function of 2 variables, we can write the f as z. So I could also write this as zx. All right, so we have these common notations to represent the partial derivative with respect to x. So we could similarly write the partial derivative with respect to y. All right, let's do another example. So let's say we have a 3-variable function this time. There's an x, a y, and a z, and I want to find all first-order partials. So first order means I'm not doing any second derivatives, and we'll talk about how to do that in the next video. Okay, so let's begin with the partial with respect to x. So I'm going to practice my other notation. I'll write gx like this. Remember, that just means del g del x, the partial derivative of g with respect to the variable x. All right, so to take the derivative of e to the x over y first, I'll get e to the x over y, and then I have to multiply that by the derivative of the exponent. Okay, so to take the derivative of the exponent, because I'm taking the partial with respect to x, that means we're treating y as a constant. So I could move the y sort of in front of this and get 1 over y times x. And when I'm doing this, I'm thinking of the 1 over y as a constant. And if I do that, I don't need quotient rule for this derivative. The derivative of x is just 1, and then that constant should just stay there in front. So I'll just get 1 over y. That's the derivative of x over y when I'm taking the partial derivative with respect to x. Okay. And now to take the derivative of 3z, well, there's no x's in that, so I'm treating z as a constant. So the derivative of 3z is 0. And then if I take the derivative of yz to the 4th cosine x, I treat the y and the z as constants, and the cosine x is the variable thing. So the derivative of cosine x is negative sine x, so I'll get minus yz to the 4th, minus yz to the 4th sine x. And that's my partial derivative with respect to x. All right, so next let's do the partial with respect to y. So again, I'll get e to the x over y times the derivative of the exponent, the partial derivative of the exponent with respect to y. Okay, so if I'm taking the derivative of the exponent, the partial derivative of the exponent with respect to y, that means I'm treating x as a constant. So because x is a constant, I don't need quotient rule again. I can rewrite this as x times y to the negative 1 if I bring the y up to the numerator. And then x is going to get treated as a constant here. X is going to get treated as a constant. X is now getting treated as a constant. So the derivative of this is going to be the negative 1 will come in front. I'll get negative x. X is a constant, and then I'll get y to the negative 2. It's just power rule. All right, the derivative of 3z is still 0 again, that partial derivative, because I'm taking the derivative with respect to y, which means I'm still thinking of z as a constant. And then for the rest, z to the 4th cosine x is a constant, so I just end up leaving that there, and the derivative of y is 1. So I'll get plus z to the 4th cosine x. Right, so that's my partial with respect to y. So finally, we have to do the partial with respect to z. So for the partial with respect to z, now there's no z in e to the x over y. So that derivative, that partial derivative, is just 0. So that actually was the easiest one to do. The partial of 3z would be just plus 3. And then in the next term, I treat the y and the cosine x as constants. And then I take the derivative of z to the 4th. So I'll get the 4 coming down, and then I'll get y z cubed cosine x. And that's my partial derivative with respect to z. And actually, you know what, this one's easy enough to simplify. Actually, all of these would have been easy enough to simplify. So something like 0 plus 3, I could add those together and just get 3. And I could have done that in all of these where I had the 0. So in the next video, we will talk about how to compute second-order partial derivatives.